to change, and also you're going to get some reward. But even if you don't pull them, their state is going to change, and that's why restless is coming from. The classical problem, the state of the bandit is changing only when you pull the arm. In the restless version, it changes also when you don't pull the arm, and the bandit is resting. Okay, so we have think about. So how do we translate our problem into the multi-arm bandit? Think about the aircraft as the bandits. Think about the resources as limiting the number of arms that we can pull in every time. And think about rewards that going to be capturing the fact that if you are below the threshold of 100, you are considered mission capable, and if you are above it, you can still fly, but you're not mission capable, so maybe we're going to give you a reward of 0.2. And if you're in maintenance, I cannot do anything with that plane, and then the reward is 0, right? And basically, by pulling the arm, that means that you either maintain the aircraft, and maybe not pulling it means that you are not maintaining the aircraft. And again, there is some more nuance here. You can actually think about different indices separately for maintenance and flying. So you can think about the arm maybe having multiple modes that you can sort of pull an arm, not only just pull or no pull, but maybe pull one mode, second mode, third mode, or whatever, right? And what we know about this family of models is that index policies are often near optimal, but there are also multiple known ways of how to calculate index policies. One of which is by taking the problem that I just described, and without getting into too many details, formulate a linear programming relaxation of the problem. That essentially what it does, it looks on the long run behavior of the system, and it translates and relax constraints that hold all the time to hold on average. And basically here, we can never violate the capacity constraint, but now we're going to say that we're going to violate the capacity constraints. We are not going to violate on average. And we cannot, we have to satisfy the flying demand all the time, every day, but we're going to just say that we're going to satisfy it on average, right? And when you actually look on this linear program, you can actually use the reduced cost, which is the equivalent of the dual variables of this linear program. For I'm sure most, if not all, the audience heard these terms, so I'm not going to spend too much time redefining them. You can actually use that to actually get indices, and that's what we did. And these are the indices that we got for both flying and maintenance. And one of the things that we realized when we did that is this concept of heavy hitter. These were, if you think about the first picture that I showed you about all the small red dots on the plane, think about like a very big dot that was a serious hit to the coding, that just by fixing it, you could actually improve the coding significantly. And it turned out that some planes had very concentrated damage, and some others had namely they had a heavy hitter, and some others had actually very little of, a lot of small damages, right? And actually what we could see that the index policy actually captured this notion, maybe sort of captured the intuition that actually maintaining heavy hitters is maybe something beneficial, because in a relatively small amount of time, you can actually reduce the SAS score quite a lot. So in order to estimate the effectiveness of this policy, we actually simulated it against real data. And what you can see here is that basically, if I compare it to the current policy, and if I actually look on different levels of maintenance capacity, then our policy, the index policy, is actually dominating the current policy. And in fact, the more the capacity is constrained, the more we actually dominate the current policy. And what you see here in the brackets, these are the resulting mission capable rates. So actually, it's known that the current mission capable rate of the Air Force in the US Air Force currently is actually around the 70%, and in some aircraft is even below that. And what you can see here, that even with the existing capacity, by doing a smarter job and a more intelligent job, you can actually increase with the same level of resources, you can increase these mission capable rates quite significantly. But the other nice thing about this work was that you could actually take the indices and translate them into very interpretable rules that you can actually communicate to operators. And again, without getting to all the details here, these operating rules, you see some of them were intuitive to them and some of them were not intuitive to them, but then they could actually think about them and convince themselves that that's actually the right thing to do. One of the major insights that came out of this work that you can actually, you're going to benefit a lot of not making the flying and the maintenance decisions separately. Currently, these decisions are made by two different organizations, by two different teams. First, the team of that decides what airplanes to fly, and then the team that decides the which airplane to maintain, and then you get something that's suboptimal if you actually make the joint decisions. So again, hopefully you see an example of something that has technical core, but has a lot of other issues that you have to address in order to actually be able to get to an end-to-end implementation. And I think I'm just about time to open it up for questions. If you don't mind, I'm going to stop sharing now so I can actually see